there, this is Dr. John, your physics and math professor, coming to you with another parabola problem. This one is about a diver, which we're going to calculate sort of backwards. In most cases, what we have is we have the initial velocity coming off a diving board or a hill or on the level plane. However, in this case, what we're given to us is the final velocity, the velocity of impact. I've written out the problem there for you. Let me just sort of basically read it off to you. Here we have a diver, and she's diving off a diving board and hits the water here, which is 3 meters below the diving board. So the water, this is a 3-meter board, and she hits the water at 75 degrees to the horizontal, which is just about straight up and down, and at a velocity of 8.9 meters per second. What we're supposed to try to calculate is with what velocity does she leave the diving board. We want to know both the initial velocity, the number, the magnitude, as well as the direction. What's the angle that she leaves the diving board at? Now, this is a little bit more of a complicated problem, and so we're going to approach this, we're going to tackle this piece by piece together, and hopefully by the end of it you'll be able to rewind this and do this problem yourself. When you're doing a problem like this and you're reading off the problem, one of the first steps is to draw a picture. I've drawn a photorealistic picture here of the dive, so hopefully this helps you here. I've already taken some of the conditions given in the description and written it up here. However, you're going to have to do that as your first step. And then often the second step in these projectile problems is to take the velocity, the impact velocity or the takeoff velocity, and divide it into components, an x component and a y component. Because of the way that we've set things up, the x component is independent of the y component. The x component has no forces acting on it and will continue on indefinitely until the object lands on the ground with the y component of the velocity. That's what stops the x component. And so what we're going to try to do is find both the x and the y component taking off so that we can get the vector that we need here. So let's start off by dividing this component, the landing component, into x and y components. I'll draw a little sketch out for you. Here I've sketched out this diver here just as she hits the water, and the angle at which she hits the water is 75 degrees. And we've taken this component here, which is our component v, we'll just call that v right here, and going to divide it into an x component and a y component. Notice the way that I've drawn it up here. We have a very nice right angle triangle right here, just like that. And so we can actually use trigonometry to find the x value here. This would be the vx, and the y value as well. So what would it be? Since this is the angle here, then we know that cosine of 75 is going to be equal to the adjacent, which is vx, over v, which is the hypotenuse here. If we want to take this v here, move it to the other side like this, then we have vx is equal to v times cosine 75. I'm going to rewrite that here at the top of the board. So I've rewritten this one up here, and then I'm going to do the other one, which is this one over here, which would be vy, the y component, the up and down component. As you can see, that would be the sine of this. So we're going to go sine 75 is equal to vy over v. And we can again take this v and multiply it over there. Now we have a relationship here for this. I can erase this here, and I'm just going to write this up here, and we'll do these calculations. Now I've written out vy, which is v sine 75. I just copied that from below here. I've actually taken the liberty of writing the numbers in there. 8.5, that's this velocity right here, times sine 75, and I've just multiplied that out, 8.5967. And the same thing here for the cosine, 8.5 times cosine 75, the answer is 2.3035. As you notice, since the elevation is pretty close to 90 degrees, it's pretty close to straight up and down, the one that's going to be the bigger one is going to be the y component, because you have more of the y component in there. So this sort of makes sense. I'm going to take these two values and write them in there. However, we should also look at significant figures. Notice here we have 2 significant figures and 2 here. Here we have a lot more. We just wrote out what our calculator got. You don't want to keep that many, but you'll want to, throughout the calculation, keep at least one more than you have in your initial question, because when you do your final answer, of course, you'll want to put it into the correct number of significant figures. But during your calculation, keep at least one more, because that's going to keep you from having a bunch of rounding errors. Let me write that in here. This is going to be vx, and then vy is equal to, this over here has to be 8.60. There's no really other way to make that. These are both meters per second. Meters per second. There we go. We have now broken down the velocity, even though it's the final velocity, into x and y components. Now we're going to find out how do we figure out the velocity here as we take off. To do that, we're going to have to break this into two pieces. So over here, I've sort of redrawn this sketch here. And what we're going to do now is we're going to focus exclusively on the y velocity, the 8.60. And we're going to try to figure out how to take that y velocity that we have here and move it back step by step. I'm going to divide this right here into two different pieces. Remember, even though I drew this like this, I'm just thinking of it going straight up and down. So let's think of this diver here. What if instead of having her dive like this all the way in, we just have her jump straight off a platform, straight down until her velocity in this direction is Vy. So she's going to start off up here with an initial velocity equal to 0 and land here with a velocity Vy. Can we calculate this distance, how high this is? Because obviously it's going to be higher than 3 meters. How are we going to calculate that? Well, to do that, we're going to need some of our motion equations. Our motion equations for constant acceleration. I'm going to write those down here. What I would suggest when you do these problems is that you look at your sheet. You'll have your study sheet with your 3 or 4 different equations, and then just with your temporary 10-second short-term memory, write them down. That's going to help you to get those things into your mind. You may never memorize them because you may be given them on your exam. Some teachers do, some teachers don't. But you will be able to have a much clearer sense of those equations because you've been able to write them down with short-term memory several times. And then after that, you can look at them all together here when you have them ready. From those equations, you'll want to pick out the one that you'll be able to use. Give me a second. I'm going to write down some equations right here. Here are a couple of different equations. We have the average velocity is equal to the initial velocity plus the final velocity divided by 2. We have the final velocity equals the initial velocity plus acceleration times time. Those are straightforward expressions that you probably can understand fairly easily. This one's a little bit harder to understand. You have the distance that something goes is equal to the initial distance plus the initial velocity times time plus 1/2 acceleration times time squared. This one's a little bit harder to understand, but you have to remember that all the velocity and the acceleration are all in the same direction. In the x direction or all in the y direction, and this would be an x value or a y value or whatever you have in that case. This is the one that's a little harder to understand. It's where the final velocity squared is equal to the initial velocity squared plus 2 times acceleration times distance. However, that's the one that we're going to use for this. This is one that we're going to develop in another video, but for now, just sort of get used to using it and realize that it's a very, very good equation to use. However, it's often important in this case to make sure everything's in the same direction. Your acceleration, your distance, your velocities, so that you don't have your negative sign being killed with a squaring here. So what we're going to do is we're going to sort of reorganize this. What if we take the diver here and have her just jump off a platform straight here, whatever height this is. I'm going to label this height D, which is this height she would jump from, so that she acquires this velocity, Vy. Well, in that case, we have an equation because we know what Vy is. It's right here, 8.60 meters per second. We have an equation that will help us with that. The final velocity right here. Let me rewrite that over here. We have the final velocity squared is equal to the initial velocity squared plus 2 times acceleration times distance. Now, in this case, since she's jumping straight off here, straight down, there's going to be no initial velocity. So we don't need that term. We can erase that term and just be left with this. Final velocity squared is equal to 2 times acceleration times distance. So her velocity is going to be in this direction when she's finished. The acceleration of gravity is down. The distance is down. Everything's in a positive direction. We want to solve for this D here. So let's do that. And we'll move 2A to the other side. And we'll have D, I'll make it a big capital D like I had here, is equal to Vf squared over 2 times acceleration. Well, the acceleration in this case is G, since that's the only accelerating acting downward. So if we can get this value here, we can find this total distance. I'm going to write these things up here, and then we're going to do this calculation. Here I've written up this equation again, Vf squared over 2G. Remember, we're just jumping straight down from here, from this unknown height D, to achieve this final velocity. And we're going to have 8.6 squared over 2 times 9.8. Now, you'll always do an estimate if you can. Notice this is about the same value as that, so let's cancel one of those. So it's going to be 8 over 2, or about 4. Let's actually do the calculation and see what we come up with. I am getting 3.769 meters. Again, we have far too many significant figures. Let's keep one more and make that 3.77. There we go. Now we know that the total height to drop from to achieve this velocity, the y component of velocity, is 3.77 meters, which means that this distance here is 0.77 meters. That's the distance above the diving board. So now we'll do the other portion of this. I'm just going to redraw this really quickly here so we remember this data, and then I'm going to do the last part of this equation. Here I've redrawn this sketch a little bit, saying that the board is 3 meters above the water and the total height is 0.77 meters above that. Now let's take a look at this. We have this sketch here of the fact that her total height is 0.77 meters above the diving board. Well, now, what if we think of her as jumping off some platform that's that high, 0.77 meters? What is her up and down velocity when she hits the diving board? Because that's the way that we can envision this, because that will give us the y velocity. Because if she jumps off something here to land there, that y velocity would be the same as if she had to leave this way and rise that high. We're just sort of switching around, and we're going to use this equation again to figure it out. Here's the equation that I promised right down here. We want to know the final velocity, only the y component of the velocity, because that's all we care about. And to do that, we're going to say she's jumping off some platform that's 0.77 meters higher, and to see what that velocity, the y component, is. Well, in that case, this is going to be 0, so we don't need this term. This is going to be 0, and we'll just have this term. So we can use this over here to calculate that. We can have VF squared is equal to 2 times 9.8, acceleration of gravity again. Everything's going down in the same direction, and d is 0.77. Well, I am getting from that, after taking the square root and doing all this, I'm going to get 3.88. Again, that's meters per second, and we're keeping 3 significant figures. So this is the y velocity at which she hits the board or she leaves the board, either way, however you want to view it. Now we're going to take these two things. We're going to take this 3.88, which is this component, the y component here, and this Vx when she leaves the board and impacts the water here, that never changes. We're going to set up a vector and get to the components for that. Here I've done a sketch of the diver taking off from the board at an angle theta. This is what we want to discover, and we want to figure out what this velocity is here. And we have found the x component, which is 2.30, and the y component as well, which I wrote over here, 3.88. We can get this v here by using Pythagoras' theorem. That would just simply be 2.30 squared plus 3.88 squared, and then we're going to have to take the square root of the whole thing. It's probably going to be bigger than both of these, so it's probably going to be about 4 or 5 or something. Let me punch that into my calculator and see what I get. I am getting 4.51 meters per second. This is the velocity at which she takes off from the board. Now though, since we're getting to the final answer, let's do this in 2 significant figures like we had here with our original question. So I'm going to make this as 4.5 meters per second. So the velocity is going to be equal to 4.5 meters per second. Draw a box around it, make sure it's clear to your teacher what your answer is. And then there's one more piece that we want to do for this. Obviously, we want to know what this angle is. And you notice you have the adjacent, you have the opposite, you also have this here, the hypotenuse, but let's use the ones that we originally have so that we avoid more rounding errors. And how do we do this? Well, we have the tangent for this. And that would be this. Tangent theta is equal to the opposite, 3.88 over 2.30. This is going to be a number a little bit bigger than 1. And the way that you do this is you look at your calculator and you're going to have 2 buttons. I'm going to erase this and I'm going to point out those buttons for you in case you haven't used those a lot. All right, on your calculator, you're probably going to have a button that says something like arctan, ARC-tan, or tan to the -1. This may be on a button itself, or it may be a very small, different color script that's above it. You may have to use a function to get that. What this does is sort of undoes the tangent function. So what you'll do is you'll calculate this number, it would be 1 point something, and then you'll do the arctan or the inverse tan of that to find the angle. When I do that on my calculator, I'm going to get the angle being 59.01 degrees. And now we're getting close to the final answer, so we want to go down to 2 significant figures. So we're going to go down to 59. And I'll write that up here. Theta equals 59 degrees up from the horizontal. Hopefully that's not too small for you to read. When you're doing your final answer, make sure you clearly indicate to your teacher that and write out your answer often too, saying the diver, she takes off with a velocity of 4.5 meters per second at an angle of 59 degrees up from the horizon. That way you have the correct significant figures and you have the entire answer written out. I hope that helped you. This was a little bit of a complicated problem, but I hope that helped you. And if it did, like and subscribe and check out my next video. I'll talk to you soon. Bye-bye.